Welcome to today's lecture. Last week we stopped with path simulation and the general idea of how to value an option using Monte Carlo simulation. I told you how the basic idea of Monte Carlo simulation works. Monte Carlo simulation is just another word for simulating random numbers from a given statistical distribution. And this is more or less what we are trying to do here. We are trying to simulate random numbers from a given stochastic process. Might be a Brownian motion, might be a geometric Brownian motion. And using the simulated returns or the simulated asset paths, we'll insert them into the option payout profile. We'll get simulated payouts of the option, and then we'll just take the average of those payouts, discount them to the present day, and then we'll have an estimate of the option price. So we'll start with the stochastic differential equation for this diffusion process, very general diffusion process. You might remember that for the diffusion process, the change in the asset price is given by a drift times the change in time plus a diffusion parameter, also a volatility parameter, times the change of a Wiener process. And the change in the Wiener process is, as you might remember, how is the Wiener process defined? As a stochastic process, aka a set of random variables with independently normally distributed increments. So the changes in the Wiener process are just independently normally distributed, and this is the very basic building block for any stochastic process. So this is more or less just a stochastic process with normally independently distributed changes. That also includes a drift, and the changes, the diffusion is also governed by a parameter, in this case B. Now, the simplest way of discretizing this, of using this process in continuous time and using it in discrete time with discrete changes in time, is via the Euler scheme. That is, just instead of dst, using delta st, and the discrete change is just st plus delta t minus st. So it could be the stock price in 2 days minus the stock price today. Then dt would be 2 days, 2 days change in time. And then we just have, for example, no need, S3 minus S0, for example, here. Then this would be the change in time. Okay. And how can we discretize the stochastic process? We would just take the drift times the change in time plus the diffusion, and from the change in the Wiener process from dWt, we know that this is, or this can be approximated by square root of delta t times a uniform, a standard normal distribution, epsilon. Now, this discretization obviously leads to a certain error, to a bias in this estimation, and with the help of Ito's lemma, one can show that there is a slightly better way of doing this. We start again from the geometric Brownian motion, d ln st, the change in the logarithmic price, which is also equivalent to the log return. And the log return is given actually by the drift minus half the diffusion squared, the volatility squared, the variance, times dt plus sigma dwt. And I've told you this last week, it's not really important how you discretize this. What is important is what we get in the end. It can be shown that you can simulate from a geometric Brownian motion, and you can exactly integrate it by this formula. St is equal to the starting point, S0, times the exponential function with this term here in brackets. So to simulate, you only need to simulate from a standard normal distribution. This is epsilon here. And if you have simulated from epsilon, you just take delta t, the change in time. You need those parameters nu and sigma. And you insert your simulated returns here. These are parameters. Delta t is deterministic. You know delta t. If you're looking at daily returns, you know that the change in time from one day to the next day is 1 day. This is trivial. So nu and sigma, those are parameters, those are given. Square root of delta t and delta t, they are also known. The exponential function is known. And you're looking at the next stock price under the assumption that you know the previous stock price. So you start, for example, here at S0, then you calculate S1. Then in this case, this would be S0, this would be S1, and then of course you know S0, and this is the only thing that changes. You only need to simulate from the standard normal distribution, insert it into the formula, and then you can simulate the next step and the next step, and you will go from here, and then to here, and so on. Obviously, these should be the same delta t's. Let's make it better, maybe. And like this. And if you have looked through the slides, this is how it is done in MATLAB. Actually a very simple program. You need to start with one price, S0, and in the example later on we'll start at 50. You have to simulate from the normal distribution, from the standard normal distribution, and this is done here in rand n. This is the standard function in MATLAB to simulate from a normal distribution, from a standard normal distribution. And then the next path step is just the previous one times exponential function nu dt plus sigma dt times epsilon. And then you'll get what is shown on the next two slides. We'll simulate 3 paths from the geometric Brownian motion, and it will look like this. And here, again, you can see why someone had the brilliant idea to use the geometric Brownian motion, because it does resemble the evolution, the time evolution of a stock price. It's completely random, of course. You're simulating random numbers from a standard normal distribution, and there's no economic background here, no economic rationale to justify that this particular geometric Brownian motion with these parameters is explaining the stock price, but it's a well-suited and well-fitting econometric and statistical model. So we have 3 paths from a geometric Brownian motion. What do we do next? We simulate 100,000 and insert it into the payout profile. So that's the next step. And we're now doing it with some additional examples for options and derivatives. And we'll now take a European-style exchange option. An exchange option is defined on 2 underlyings, u and v. We'll assume a geometric Brownian motion, actually a 2-dimensional geometric Brownian motion for u and v. We could have also used 2 geometric Brownian motions that are independent, but we are now including a 2-dimensional one that is simply a geometric Brownian motion that is linked to another one with a correlation of rho. The payout profile at the time of maturity is the maximum of Vt minus Ut or 0, meaning you're looking at 2 stocks, at 2 stock prices, and you're being paid out the difference between the first and the second stock or 0. So let's say, for example, U is BMW, and this is Daimler, and the payout profile means that if this is the BMW stock price and this is the Daimler stock price, you're getting paid this difference. This is why it's called an European-style exchange option. It's not a plain vanilla option, but a style exchange option. It is a special case of a spread option. Why? Because obviously you're being paid out the spread between the 2 underlying prices. Well, this difference is referred to as a spread. Okay. Now, in this very simple case, you could still probably guess, and you're right if you've guessed this, that this is still a very simple option, and it can be priced via Black-Scholes. There is an analytical solution in the Black-Scholes model for such an exchange style option. And the analytical solution is given by the price is V0 times n d1 minus u0 times n d2, d1, d2, and sigma hat as defined in here. Meaning that under the model assumptions of the Black-Scholes model, you do not need Monte Carlo simulation. You can simply plug in your parameters and your market parameters into this analytical solution and this pricing formula. However, we are doing it anyways to show what the differences are between Monte Carlo simulation and Black-Scholes. Because ideally, we would think that under perfect model assumptions, the Black-Scholes price will be the correct one. But we'll see how good Monte Carlo simulation can actually be later on. Okay, now this is the analytical solution. We are simply taking the Black-Scholes pricing formula and programming it in MATLAB. As you can imagine, it's quite simple. P is V0 times norm CDF D1 minus U0 times norm CDF D2. D1 and D2 are defined in lines 3 and 4. Sigma hat needs to be computed before that. So you take the square root of sigma squared plus sigma squared minus 2 times rho sigma 1 sigma 2. This is very simple. Now, for Monte Carlo simulation, what do we need to do? We need to simulate paths from a two-dimensional geometric Brownian motion. In this case, we simulate two standard normal distributions that are linked via a correlation rho. And this can be done quite simply. Epsilon 1 is just a random number from a standard normal distribution, Z1. And if we do it twice, we'll get two stochastically independent standard normal distributions. But we want them to be dependent. We want to have two random variables that are linked to each other with a rho, with a correlation coefficient. So to simulate from a two-dimensional standard normal distribution with correlation rho, you need this formula. Epsilon 1 is Z1. And then you'll take epsilon 2, and epsilon 2 is rho times epsilon 1 plus square root of 1 minus rho squared times Z2. So you simulate twice from a standard normal distribution, and you calculate epsilon 1 and epsilon 2 via this formula. And then we know to discretize the geometric Brownian motion, we take st times exponential function u delta t plus sigma square root delta t times epsilon. We insert it, and this is obviously the reason why it's still a plain vanilla option. The price of the option at maturity, the payout, is not path dependent. We can see that those two prices of the underlyings, then they can go either way, or it could also go this and this, but in the end, only this difference matters. So it's a plain vanilla option that is not path dependent. So we only need to determine the terminal value of each simulated asset path at time capital T. This is the only thing that matters here. So let's do it here in MATLAB with Monte Carlo simulation. It's a function P and Ci, that's the output. I mentioned this last week. We want the price as an output, and we want a confidence interval. Ci is meant to be a confidence interval around the price, and we want to see how this confidence interval decreases with an increasing number of simulations. So the function is called exchange MC. We have as input parameters U0 and V0, the starting prices of the underlyings, sigma V, sigma U, rho, the maturity capital T, R, the interest, the interest rate, and N REPL, the number of replications, the number of simulated paths we need. Epsilon 1 is rand n 1 n REPL. Epsilon 2 is rho times epsilon 1 plus square root 1 minus rho squared times rand n, again, with the n REPL as the number of simulations we are running. So if we set n REPL to 10,000, we're using 10,000 simulated asset paths. If we are using just n REPL equal to 10, we'll only have 10 simulated asset paths. And then VT and UT. Remember, we need 2 simulated paths from the 2 underlyings. And this is just what we would do for any geometric Brownian motion. We discretize it, we simulate its path, and we get VT and UT. And we only need the final value because we need to compare VT and UT to get the payout of the option. And disk payoff is referring to the discounted average payoff. So not the average, but first the discounted payoff. So we'll take the payoffs of the option, which is the maximum of VT minus UT or 0, and then we discount it in this continuous time. So exponential function of minus R times capital T, that is just the discount factor. So disk payoff is a vector of n REPL times the discounted payoffs of the option. And then normally we would just take average mean of disk payoff. But here we are doing it slightly more sophisticated, in a slightly more sophisticated way. We'll take the discounted payoff and we'll fit a normal distribution to it. And the normal distribution here, the norm fit function, does not only yield the average, the mean, but also the standard deviation and a confidence interval around the mean, assuming a normal distribution of those simulated values. And this is just a nice way to show how far those values are spread around the average, around the expected value. And in the examples, you'll see what happens. So let's do a short example. We'll start with 50 for the first underlying and 60 for the second underlying. We'll assume a sigma v of 30 and sigma u of 40%. We have correlation of 70% and 5 months and an interest rate of 5%. From the Black-Scholes model, we know that the analytical solution is 0.8633. Now we'll run a Monte Carlo simulation with 200,000 replications. And the average result here is 0.8552. And the lower and upper limit of the confidence interval for 95% around the mean is 8.444 and 8.660. So with 95% confidence level, the true price given by the Black-Scholes model under these assumptions is within the confidence level and this confidence interval. So this very simple approach, just take the geometric Brownian motion, simulate enough paths, plug it into the payout profile, and calculate the mean discounted payoff, gives you a price that is actually quite close to the assumably true price given by the Black-Scholes model. Why is this the case? This is no coincidence, but why? Why is Monte Carlo simulation so close to Black-Scholes? First of all, yeah, any ideas?
I'm looking at the input parameters or the assumptions are closely to Black-Scholes.
Yeah. In both cases, we're assuming the same stochastic process, geometric Brownian motion. And let's be honest, this is the most pivotal assumption you are doing. You need to have some idea how the underlying price evolves in time. And if you're assuming the same stochastic process, both in Black-Scholes and Monte Carlo simulation, it's not a big surprise that those two prices match. Secondly, the remaining assumptions and parameters also match. And in Monte Carlo simulation, you are assuming that today's price of the option is given by more or less the expected value of the discounted payoffs. And this is close to the idea of a neutral, risk-neutral pricing and arbitrage-free pricing you also have in Black-Scholes. You're using the same parameters, you're taking the same assumption on the stochastic process for the underlying price, so it's not such a big surprise. And if the assumptions of Black-Scholes are true, you will see that Monte Carlo simulation will yield prices that are actually quite good. In reality, however, the assumptions can be violated, but if the assumptions hold true, if the assumptions hold, and you have an option that is path dependent, that for which you do not have a Black-Scholes formula, then Monte Carlo simulation is a viable option. Okay. And of course, you can drive up the number of simulations, and you will see that this confidence interval will grow smaller and smaller around the mean. Okay. Now let's do next a Monte Carlo simulation with a barrier option. A barrier option is referred to as weakly path dependent. Why? A barrier option is an option that is more or less a plain vanilla put or a plain vanilla call, but this plain vanilla put or call comes into action or is knocked out in case the underlying price crosses a limit, crosses a barrier. And you can differentiate between down and out and down and in, or up and in and up and out options. So you have knock-in and knock-out products. Knock-in options are those options that only become active after the underlying price has crossed a barrier, and knock-out products is the opposite. It's a plain vanilla option that is active and can be exercised only until the underlying price crosses a certain barrier. Then it's knocked out and it's invalid. And we'll now look at a down and out put option. For this put option, you also have a Black-Scholes price. The price, first of all, for this put option, the price is given by the price of a regular put is equal to the price of a corresponding down and in plus the price of a corresponding down and out option. So you have something that is similar to the put-call parity, but in this case you have a parity between a down and in plus a down and out put option, and the prices should be equal in sum to the price of a regular option. And in Black-Scholes you also know how the down and in and down and out prices should look like. Here on the last three lines, you can see the Black-Scholes price for a down and out put. Don't memorize it. Yeah? You don't need this. If you are ever in need of such a formula, you can simply look it up in a textbook. But as you can see, it is slightly more complicated than a regular put, but it's still Black-Scholes. You need the standard normal distribution. You need to calculate D1, D2, D3, D4, D5, and so on. And again, afterwards, you simply plug it into the formula, calculate the price, and you have your Black-Scholes down and out price. This is how D1, D2, D3, and D4 look like. They are almost the same. You only have some signs that change. And again, you can see why it's called weakly path dependent. The price does not fully depend on the path of the underlying. You only have the additional possibility that the price of the regular put suddenly is zero because it's knocked out, or that it changes from zero to the price of a plain vanilla put if it's knocked in. That's why it's called weakly path dependent. But otherwise, it's just a simple plain vanilla put. The MATLAB coding is not very interesting. As you can see, you simply need to program all those 8 Ds And afterwards, in line 13, you plug it into P, which is the price function. Yeah? K times exponential, the discount factor, times ND4 minus ND2, ND7, ND5. Okay, this is not that interesting. Do you have a question?
Yeah, can a vote option that has been knocked out be knocked in again?
No, usually not. That's why it's called no. It might be that there are some products that can also be knocked in, but that doesn't make, I don't think that makes too much sense, because in that case you will simply get a regular put. What might be, I mean, a down and out option that can again be knocked in is just a regular plain vanilla option that is out of the money. If it's out of the money, its value is 0, and its value can appreciate in case the underline goes up again. So that wouldn't make sense. It might only make sense if you have different barriers. If you have a strike and a knock in or knock, but then you just have a knock in or knock out product again. I don't think you can think of it. If you want to financially engineer it, you can do it, but I don't think that this type is traded. You know? So if it's knocked out, it's knocked out. Now, again, we have a Black-Scholes pricing formula. We know the analytical price under the Black-Scholes model assumptions. And again, we can do it in MATLAB with Monte Carlo simulation. However, as you can imagine, this is now trivial. Take the same function to simulate from a geometric Brownian motion, plug it into the payout profile, calculate the discounted payouts, average them, and you get your price from Monte Carlo simulation. Now with this option, you can only see that it's slightly more complicated when we get to the programming. Why? Because we now need to simulate the path, and in every step we need to check, has it crossed the barrier yet? No? Okay, go further. If it has crossed the barrier, stop. If it's a knockout product. You know? And this is here done, for example, in lines 9 through 13. If crossed is equal to 0, payoff I is the maximum, blah, blah, blah. Else payoff is 0. N crossed, just jump to N cross plus 1. Or actually, no, this is N cross. Okay, I have to explain this. Let's go through this program line by line. First of all, we're interested in the price and the confidence level, confidence interval, but now also in a number N cross. We'll later on see what N cross is. We have all those input parameters, that's okay, and we generate our asset paths. We start with N cross equal to 0 in line 5. Then, for every number of simulation, path is asset path, that's our help function we defined before to simulate from a geometric Brownian motion. And then what we do now, crossed equals any path lower than or equal to SB. SB is the barrier. Meaning, crossed is a vector that shows you all those underlying prices that are below the barrier. And if crossed is equal to 0, meaning that the barrier has never been crossed, the option has not been knocked out. So the payoff is a maximum of 0 and the strike minus the last underlying price. If else the asset path has gone below the barrier at least once, and in lines 12 and 13, payout 0, N cross plus 1. So this is the case that the barrier option has been knocked out, and we increase N cross by 1, and N cross later on will tell you how many of those simulated paths the barrier option was knocked out. So for example, if we have 1,000 simulations, and n cross is 350, we know that in 350 cases out of those 1,000 simulations, the barrier option was knocked out. And then, in the end, you know how this goes, non-fit discount factor times payoff gives you the Monte Carlo price. Yeah? Simply take the payouts and discount them and fit a normal distribution, or you could take the mean of it. And here, this is one run of this. Down output, again, 1.3629 is what? The Black-Scholes price. And then we do DO, down and output, MC, with 100,000 simulations. And the price we get is 1.3597. So actually quite close to the Black-Scholes price. And N cross is 14,439. So actually we do know how many times the barrier was crossed in 14.43%. So out of those 100,000 simulations, in 14% of those simulations, the barrier was the option was knocked out. Just a slight gimmick, very handy additional information. And this is the valuation of a barrier option. Again, not really necessary because we have a Black-Scholes price, but just to show this is quite nice. We can also use correlations and build them into the random samples to improve the Monte Carlo simulation. And this is used to reduce the variance of our estimator. So we're now looking at conditional Monte Carlo simulation. First of all, we start with the equation that the down and out price is equal to the price of a regular put minus the down and in price. Now, we assume we divide the term of the option into intervals of length delta t, so that we have n times delta t. An underlying path is then given by S1, S2, S3, up until Sm. And then we estimate the option price using, again, discount factor, and then the expected value of the option payout, K strike minus the final underlying price. If it's positive, this difference, otherwise 0, and an indicator function. And you know that for the barrier option, we need an indicator function that is 1 if the barrier option has been knocked in at least once, or 0 otherwise, if it has not been knocked in. Okay. So this is the indicator function. And first of all, we do just a regular Monte Carlo simulation. And this is the same, it's a down output, and we get 1.3597. And now let J star be the time index at which the barrier is crossed for the first time. We set J star equal to m plus 1 if the barrier has not been exceeded during the term, so the option has not been knocked in. At this time, J star times delta t, the option is activated. And after that, the option is just like a regular put, like a plain vanilla put. So given this threshold on this crossing time, J star or T star, and this price at this moment, we could also have used for this down and in option the Black-Scholes price. So we can use the additional information that if for a down and in option, the option has been knocked in, we don't need to simulate any further. We only need this point in time, and then we can take the Black-Scholes price. So what we are doing now is, we are not doing the plain, or not the plain vanilla, but the regular Monte Carlo simulation. We are still simulating average paths, but we are only looking for this point in time at which the option has been knocked in. And then afterwards, we'll use not the final underlying price, but we'll take the Black-Scholes price. Because afterwards, it's a plain vanilla European put. And then we discount this over the remaining maturity from capital T minus small t, star actually, from this point. Is this clear to everyone? Probably not. So instead of using the simulation over this point or this period in time and using S star, we are simulating, and we know at this point the option has been knocked in. We know that this here, from this on, it's a regular plain vanilla put. So we'll take this here, use Black-Scholes, estimate the price of a put option in this point at J star, and we do not discount this payoff here, but we only discount BP, the price of the put option under Black-Scholes. And then we'll get this conditional mean. Should give the same result with one exception. In the first scenario, we are using simulated paths through all the periods, from 0 to capital T. But as we know that the true price should be given by the Black-Scholes price, we are only simulating the asset path now to see at which point the barrier option is knocked in, and later on we'll just use the Black-Scholes price. And this should, of course, improve our estimate. And this is the first example where we'll see that the difference can be seen in the size of the confidence interval. So we simulated paths, we can use the following estimator, and the difference now is, of course, that we are not discounting from 0 to capital T, but we are discounting from T star to capital T. So from 0 to capital to T star. And the MATLAB program now looks slightly different. Down and output, MC cont for conditional. We are generating the asset paths. Now we are not interested in the terminal values of the asset, but we only need the point in time at which the option is knocked in. So this is here you can see T cross is minus find path smaller or equal than SB. So we are trying to find the index in time at which point the option is knocked in. If not, the option has not been knocked in. Else, you can see this here, we'll use the Black-Scholes price with this here, and again we have those payouts today, those simulated payouts, and we'll fit a normal distribution to it. The difference now is what? I told you that we're interested in a down and output. Now this obviously is the pricing formula or the Monte Carlo simulation, conditional Monte Carlo simulation for a down and input. No problem. We saw that P equals PDO plus PDI, down and in plus down and output equals the price of a plain vanilla put. So later on here in line 13 you can see the price of a down and output is non-fit put minus payoff, P minus PDI. So this should give you the same. So to be precise, we use Black-Scholes twice. First of all, we are using the relation that the down and out plus the down and input equals the European plain vanilla put under Black-Scholes. And we are using the additional information that after the option has been knocked in, its price should be given by the regular plain vanilla Black-Scholes put. And if we do it now here, you can see that this is down and out put MC, and here you have this confidence interval 8589, and now we're using MC conditional, and you can see the difference 8589 8686. So the estimate changes just slightly, but you can see this confidence interval gets much smaller around the mean. And this is meant by variance reduction. You're using an estimator for the price, and this estimator has a certain variance. And the better the estimator, the lower the variance of the estimator, the better. So we are looking for a very small confidence interval here. So this is the result here. The confidence interval is reduced. Okay. Now, up until this point, we were able to use black scones. Now let's turn to an Asian option, a truly path-dependent option. We are using an Asian average rate call option with discrete arithmetic averaging. The payoff function is given by 0 or the maximum of 0 or 1 over n, sum from I equal to 1 to n of all those different stock prices, minus the strike. So you take the average of the stock price, you subtract the strike, and if it's positive, this is your payout. If not, you have a payout of 0. You assume that the prices are measured at equidistant points in time, and we now price it with a simple Monte Carlo simulation. And as you can see, it's a program in 8 lines. You simulate paths from the geometric Brownian motion, you put it into this function. The only difference to the case before now is that in line 6, you take the maximum of 0 and the mean of the paths minus k, and again you discount those payouts, you fit a normal distribution to it, and you get the average price and the confidence interval. And here we're not even showing an example. It's the same as before. The only difference is that you now do not have black scones at your disposal, and Monte Carlo simulation is the only thing you can do. But still, it's quite simple. Again, we want to improve on this by reducing the variance and the size of the confidence interval. How can we do this? Now, we want to do this by adding control variables. The general procedure for variance reduction using control variables is the following. Let's assume we intend the estimation of the mean, of the expected value of x, which in the population is theta. Another variable, y, is assumed to be correlated with x, and x has the expected value of mu. So you have x and a correlated variable y. We call this variable y a control variable, and we use the control estimator xc. This is a new estimator, and xc is given by x plus c times y minus the expected value of y mu. Why is this a control estimator? Quite simply, look at this. What is the expected value of xc? It's theta, the parameter we want to estimate. What does this mean? xc, any estimator for xc is, how is it called in statistics? Someone who's studying mathematics or financial mathematics? The estimator estimates the desired parameter theta in the population, which means that the estimator is unbiased. In German, unverzerrt. Unverzerrter Schätzer, an unbiased estimator. In the expected value of the estimator, more or less, is the true parameter. But what does the variance of xc look like? It's the variance of x plus c squared times the variance of y plus 2 times c times the covariance between x and y. Now we estimate c by minus the covariance divided by the variance of y. And we then get, I think this is not the correct translation, an unbiased estimator with a slightly lower variance than the original estimator, y. if the variance of x c star over the variance of x is given by 1 minus the correlation squared, and if we have positive correlation, you can see that rho is between -1 and 1. If you square it, it will be less than 1, but it will be positive or 0. And then you can simply see that the variance of xc star is reduced compared to the variance of x. Is this clear? So with rho unequal to 0, this means that rho squared is between, well, actually not 0 and 1. That means that 1 minus rho squared is element of 1. And if you now multiply both sides with variance x, you can see that the variance is reduced. It's quite simple equation. For a correlation that is not equal to 0. If the correlation is 0, then they will be the same, obviously. Okay. So we can reduce the variance of this new estimator. Why? Well, if you include a variable that is correlated with x, you are including additional information in your estimation, and that should yield some advantage, right? One option for the control variable could be the sum of the underlying prices. So we could choose y equal to the sum of the underlying prices. And this option and this choice is the advantage that we can determine the expected value of y. Y is obviously correlated with the option price, because in the case of the arithmetic Asian option, the payout was just the average stock price minus the strike, or 0. Another choice could be the price of an average geometric option price. For this we know a Black-Scholes price, but we now use this average. The expected value of the sum of the underlying prices is y, and here you can use this if you have a geometric Brownian motion and you take the sum of all those steps. You can get this result here, that actually you know the expected value of y, which is just the starting point as 0 times this expression here. And then you include this in your Monte Carlo simulation to reduce the variation. So remember that this is the expected value of y. This is here and y is defined as the average stock price, the sum of all stock prices. So let's do this here. We first need to set those parameters, and we do 2 simulations. The first run of simulations is only meant to estimate those control variables and the parameters. So we have tripath, we sum all those stock prices in stock sum, and then we take the averages, and here we estimate the covariance, we estimate the correlation, and later on we get C, we get DT, we get the sum of all those underlying prices, and then finally here we do the actual simulation run. We use the stock path, again we simulate. The payoff is the payout profile of the option, discounted in lines 6 and 7. But now we're doing the conditional Monte Carlo simulation with control variables, and we are not using x. Remember, we are using x plus c times y minus the expected value of y. And in this case here, this is payoff plus x. This is x plus c. This is y minus the expected value of y, or the average of y. And this here, this is xc. We could have done the same thing with just those simulated paths, but we did a first run of simulations. We calculated the sum of those stock prices and the expected sum of all stock prices. And the result will be what? Again, both programs, a normal Monte Carlo simulation and also the controlled Monte Carlo simulations, will give you exactly, almost closely the same mean option price, but the confidence intervals around those estimates will be reduced. And there you can see that control variables can be used to improve on the precision of your Monte Carlo simulation. So here you have Asian MC and Asian Monte Carlo simulation with a control variable. Again, 3.99, 3.95, but in the last line here you can see that the size of the confidence interval is dramatically reduced by including a control variable. What is the price of using the second approach with a control variable? What is the burden? Additional computational burden. You need two runs of simulation. You first run 100,000 simulations, let's see. Yeah, probably you use the same, right? You first need, actually, let me just check the input parameters. I think we used 5,000 simulations here for the first run and 45,000 for the second run. Yeah, NREPL and pilot. So 45,000 in the second run and 5,000 in the initial run to initialize the parameters. The expected sum of all stock prices and the sum of all stock prices. Computer needs more time. Your estimate of the option price will become better. That's the price you have to pay. Huh? Okay. So that's the evaluation of an option, an Asian option. Any questions when it comes to Monte Carlo simulation? Monte Carlo simulation is tricky if it's done on a very sophisticated level, because in research you will look at much more complicated stochastic processes, and you will look at much more complicated options, obviously. But in this very simple case of a geometric Brownian motion and these plain vanilla and even plain vanilla exotic options, I would call them, an Asian option, it's a very simplistic approach. You simulate until your computer breaks down, you plug it into the option payout profile, discount it, and take the average, and you get the average discounted payout of the option under all these simulations, and you have your Monte Carlo price. Any questions concerning Monte Carlo simulation? Okay. Then, finally, let's turn to option pricing using finite differences. This is tricky. However, the idea is very simple. Has anyone ever heard finite differences, finite Differenzen in German? Anyone who has studied mathematics and taken an interest in numerical analysis, computer graphics, or partial differential equations? What are finite differences? Keine finiten Differenzen. Okay. The general idea is as follows. We are still starting with Black-Scholes. Black-Scholes is the foundation. Now, as you remember, the problem with Black-Scholes was that the Black-Scholes equation was a stochastic partial differential equation. It's an equation that includes partial derivatives, and we need to solve for this partial differential equation, and solving for a PDE means we need a starting point and we need some elaborate mathematical tools to find the solution. In some cases, we cannot find a solution. And this is always the case with exotic options. We will not find a solution analytically. But what can you do? Remember that a partial differential equation is so complicated because it's a basic, simple equation that is complicated by including partial derivatives. And what is a derivative? What is the mathematical precise definition of a derivative? Of the first derivative, let's take the first derivative of a function. What is a derivative? Ja? Ja? Ja?
Der Wert einer Ableitung an der Stelle T0 ist der Grenzwert von h gegen 0 von f T0 plus h minus f von T0 durch h.
Please. Okay. Say it again. It's the limit of h to 0 for
f in brackets t plus h minus f t divided by h.
h. Okay. So in other words, it's what? It's the limit of the differential of the function at this point. You take a point if you have a function like this. The general idea is that you take 2 points, let's say x1 and x2, then obviously you have f of x1 and f of x2, and you can look at this, and if you take a function, for example, like here, you have the first derivative as the increase of the tangent to the function. How can you approximate it? By using a triangle. And the triangle would look like this. Obviously, this is not a very good approximation, but what you do is you move x1 and x2 closer to each other. So the simplest way to approximate the derivative of a function, which is of course a limit, the best way to approximate this is just to use 2 points, x1 and x2. Look at the function values, f of x1 and f of x2. Construct a triangle and use just very tiny distances between x1 and x2. Again in German. Das ist eine Ableitung. Eine Ableitung ist der Grenzwert des Differentialquotienten. f von x minus f von x2 minus f von x1 geteilt durch x2 minus x1. Wenn Sie diesen Differentialquotienten im Grenzwert betrachten, kriegen Sie den Differenzenquotienten. Nein, Quatsch. Die Ableitung ist der Differentialquotient und das ist der Grenzwert des Differenzenquotienten. Sie betrachten ja Differenzen im Quotienten. f von x2 minus f von x1 geteilt durch x2 minus x1. Und wenn der Abstand gegen 0 geht, was hier oben letztlich beschrieben ist, dann ist das die Ableitung. Und wie approximieren Sie dann die Ableitung? Indem Sie einfach wieder einen Schritt zurückgehen und Sie betrachten einfach Differenzenquotienten. Deswegen nennt sich das, was wir jetzt gleich machen, finite Differenzen, endliche Differenzen. Sie nehmen die Differentialgleichung im Black-Scholes-Modell und ersetzen alle partielle Ableitungen einfach durch solche Steigungsdreiecke. This is the basic idea of finite differences. You take Black-Scholes and you substitute all partial derivatives by differences, by finite differences. We approximate all those partial derivatives, and you can imagine that if you substitute those partial derivatives by something more similar, something more simple, you can easily solve the partial differential equation. And this is what is done in finite differences. It's a little bit more tricky because you have to look for the way how you can substitute those partial derivatives. You can take forward differences, backward differences, and some other things, and then you get different results. But this is the basic idea. We start with Black-Scholes, and this is the Black-Scholes formula, the Black-Scholes equation. And you can see those those Greeks, the option theta, the option delta, and the option gamma, and you substitute those by finite differences. And let T again be the maturity of the option, S max be a sufficiently large underlying price that cannot be reached, so that's an upper limit to the stock price, just use 1,000 euros. And we will approximate the continuous time with a discrete lattice, mit einem diskreten Gitter. And we just say we have points in time 0, delta t, 2 delta t, and capital T. So we cut it up into capital N points in time. So this is T 1, 2, 3, 4, 5, 6, 7. And at each point in time, the stock price can only be at, say, 1, 2, 3, 4, or 5 euros. Again, we are using discrete changes in the stock price. And now you can see why it's called a discrete lattice. Okay, no, it's not really nice. We get a lattice. For illustration, you can link those dots, but you can see what is meant by a discrete lattice. Yeah? And you can see now that the stock price can only move from here to, say, here, to here, and then here, or maybe to here. And this is a simplification, obviously. To make it more simple, we now denote the value of the option at point J in time with a stock price I as Fij. J is the point in time, I is the underlying price the underlying has taken at this point. And then we get the option price Fij. Those partial derivatives are now substituted by differences. We can use forward differences, backward differences, or symmetric differences. What is meant with forward, backward, and central differences? Now, if you are here, if you're at a point T, just get back. I have to go back one step. I is the stock price and J is the time. You can see that you're doing what? Remember, it's always I. For the forward difference, you're looking at the option price here, and you're taking this stock price and the next. So you have this forward difference. The backward difference is exactly the opposite, and the symmetric or central difference is just this one, and those two are averaged. Yeah? Fij plus 1 minus Fij minus 1 over 2 delta t. And then you get an approximation. In this case, this is always given for the option delta. So this is the first Greek and the first partial derivative. The second partial derivative is also approximated as follows. This is the case for the forward difference. And again, you simply substitute the derivative using differences, using triangles at the function. It's quite simple. Now we also need those boundary conditions, because still, although we have simplified the Black-Scholes equation, we need some boundary conditions to solve this equation. For a plain vanilla European put, Fin is equal to the payout profile, quite simply. If you are at the end of time, in the last column of our lattice, you know what the option pays out. F0j, which is what? You want? No? It's the extreme scenario that the stock price will be 0. That's the maximum payout. And Fmj is the extreme case, in which case the stock price has reached its absolute upper limit. Remember that we are assuming that the stock price can only move between 0 and a natural upper limit m, which might be 10,000 euros, for example. And in case the stock price is 10,000, regardless of what point in time we're looking at, j is not defined, then obviously the price of the put option is 0. Yeah? We can sell it at a much higher price on the market if the stock price has gone to the upper limit. And this is the maximum payout if stock price goes to 0 at any point in time. So those are the boundary conditions, and we can simply take a look at our lattice, and we know that, for example, let's go back here to my small lattice up here. Now, assume this is time, and this here is the stock price. Now, which points do we know? We know this, because this means that the stock price is 0, and that's the best case scenario for the put. We know this, that's the stock price taking on its maximum value, and that's, for us as a derivative investor, it's worst case, the option price will be 0. And of course we know this here. What is this last column here? What is that? The last column is?
The date of expiration.
Yeah, maturity time t, and those points are, what are the prices? They are given by the
Actual price?
By the payout profile of the option. It's a maximum of k minus the stock price or 0. This here, this is known because this here is at point t, and at point t we know the payout profile is what? It's the maximum Fij. That's the option price. It has to equal the maximum of k minus s capital T or 0. Here in this lowest line, we know that this is actually k times e and so on. And here we know that the Fij is equal to 0, because this is then the option in the most upper line, the option is worthless. If the stock price is 10,000, the option is worth nothing. Yeah? So we do know quite a lot about this lattice. We know the highest points in the highest line and in the lowest line and in the last column. And this will help us, together with an assumption that we can substitute the partial derivatives by a forward, backward, or central symmetric differences, then we can solve the Black-Scholes equation. Is this clear why we know these 3 lines in the lattice? The last column is the same as with the binomial model. We know it. Why? Because at maturity, we know what the option pays out, depending on where the stock price is. And the first and the last line, we know these because those are under the assumption that the stock price can move between 0 and 10,000 euros. We know what the option would pay out in these extreme scenarios. And then, if we all take this together, we can solve for the Black-Scholes, the simplified Black-Scholes differential equation. By the way, for a European vanilla call, it looks slightly different. We again know the last column. We know the most upper and the most lower line, but those are switched right now. For a call, obviously, if the price goes up, we have zeros in the lowest line, and we have a different payout in the upper line. Okay. Now, we first implement the solution for this partial differential equation in a European vanilla put. We approximate the partial derivatives using centered differences and the derivatives to t using backward differences. As a result, we get this expression. Now let j be equal to n together with the end condition that in the end we know what the option pays out. The value fi n minus 1 is an unknown function depending upon 3 known values. And then you have to calculate a lot. And we get an explicit scheme that is fi j minus 1 is equal to ai star fi minus 1j plus bj star fij plus cj star fi plus 1j. This seems pretty complicated. It actually is not. You don't need to memorize it, but you need to see that actually this gives you the price. Why? You know, again, just like in the case of the binomial model, you know the last column, and you can take those values from the last column, the most upper line and the lowest line, and you can simply, recursively fill those blanks in the lattice. You fill column n minus 1, you fill column n minus 2, n minus 3, until you reach the first, and then you've solved for the whole lattice. It's virtually the same idea. It's a little bit tricky when you do it on a computer, so I would urge you to do it yourself and then compare the result with the function here. We want to price a European put. You only need, as an additional parameter, as max, the maximum stock price. I would simply say 2,000 euros. And you set up the grid, the lattice, and actually this function linspace gives you a lattice. Then you need to set up the boundary conditions. You need to set up those coefficients, A star, B star, and C star. That's not very interesting. And then you have to solve this recursively, backwards in time. Take the last column, then calculate the values in the second last column, in the third last column, and backward and backward and backward. And in the end, this is interesting. You have those values in the end. And what you do then is you interpolate. You know where your stock price started, and the problem is that obviously you can only choose between one price in the end when you're starting and another one. And because it's a discrete lattice, you will have 2 prices, and this might not exactly match your starting stock price. So what you do is you interpolate, meaning you draw a line, or in this case a polynomial, between 2 points. So you have 2 points here, and you simply draw a line through it. And you take those values and you try to evaluate this at S2. For example, if S0 is here, then you know this is the price. This is why you need to interpolate here. This is the basic idea of finite differences. If you do it here, you can see that you use a Black-Scholes price is 4.076, and if you use finite differences, you get 4.0669. Second example, 2.84, 2.82. Again, only tiny differences between the Black-Scholes price and the approximation using finite differences. Again, what is the advantage of using finite differences? And why is it so close to Black-Scholes?
The formula is basically based on Black-Scholes, just...
It is the Black-Scholes formula. It's simply an approximation to it. It's a numerical approximation to the Black-Scholes partial differential equation, yes?
And it saves computational time?
No, it needs more. I would say, obviously, if you take the Black-Scholes formula and if you have an analytical solution, it's simply plugging in numbers. And you can do it on a piece of paper, and if you can do it on a piece of paper, the computer can do it in no time. Finite differences it includes much more basic arithmetic calculations. You need to calculate all those differences, and you need to set up a huge lattice. And of course, the finer the lattice is, the better your approximation will be. If you just use, the stock price can be 0, 50, 100 euros, it's a small lattice, not too many calculations, but a very bad approximation. And here, actually, I think we are using, we are dividing it by 1,200 by using a very fine grid. So if you increase the granularity of the grid, your computer will take more time. But why are we doing it? If it takes more time.
Sometimes we have another option.
Yeah. If you do not have any analytical solution to the Black-Scholes formula, you either do Monte Carlo simulation or you do finite differences. In some cases, finite differences may be faster, and in some cases, Monte Carlo simulation might be more appropriate. But it's simply an alternative to Black-Scholes for exotic options. And this is option pricing using finite differences. You can see there is one example here where it blows up. The Black-Scholes formula was on the previous slide. You can see that we are using the finite differences again, and we are now using a slightly different, what's the second parameter? I have to check that. So 1.5 versus 5. The second parameter is the step size for the stock price. So whether we take €1 differences, 1, 2, 3, or if we use 1.5 euro differences. And as you can see, we are simply making the grid slightly finer. In this example here, 1.5 versus €1, and it immediately blows up. So it is not perfect in the sense that it will always yield results. There are obviously some other numerical problems associated with finite differences as well as Monte Carlo simulation. And here you can see that in the last example, just with a slightly finer grid, it blows up. Yeah, it yields a result that is not usable. It's 10 taken to the 22nd power. That's not the option price, unfortunately. And you see that here, that this variant of finite differences can be numerically unstable. One way to avoid this is to use an implied scheme or an implicit scheme. Here you can use forward differences. You get a slightly different lattice, but I'll stop here. Why? If you now have understood the general idea, take Black-Scholes, take the partial differential equation, substitute the derivatives with triangles, with differences, finite differences. The rest is up to mathematicians. You can use different schemes. Some of them are slightly better than others. Some are numerically stable, some others aren't. But at this point, you're way beyond anything you would usually learn in a bachelor's course on risk management. So you can have a look at this implied scheme. You need to calculate more, but remember, in the end, this here is what? It's a linear function with a lot of variables. And the only difference to an equation of this type back from high school is just that you need to calculate more. You need to do more calculations on a piece of paper, but you can do this. This is not a problem. And then you get an implied or implicit scheme. It looks more complicated, and the MATLAB program is again quite complex. It's almost trivial, but you need some experience to program it. And then this is the implicit scheme here in MATLAB. Again, you need to set up the grid. You need to set the boundary conditions, and you have to code this implicit scheme, and in the end you will again get an option price. And then you can solve for this numerical instability, and this is finite differences. Again, it can be done in much more sophistication. This is something that financial mathematicians work on, coming up with more elaborate finite differences schemes for more complicated differential equations and more complicated options, obviously, but the basic idea is always the same. Take the partial derivative, partial differential equation, and substitute the derivatives. Okay. Do you have any questions? Any remaining questions for the exam? Because this is our last class before the exam. As you can see, I will not be able to look at this here. So the remaining part of the slide set is not relevant for the exam. And if you do not have any questions, yeah, you have a question.
Ich sage mal auf Deutsch, die Herleitung für das Black Scopes
ist relevant. It's relevant. If you take a look at the previous exams, I would guess that in every second exam there was a question: describe verbally or by the use of formulas the derivation of the Black-Scholes formula. It helps if you memorize the formulas. They are not that hard, and if you have memorized them and you can write them down, I'm not grading you on the precision of the formulas. If you have tiny mistakes in the formula, that doesn't make any difference. But it of course helps to use formulas, because you might be able to do it in a millisecond faster than if you write it down verbally. But if you do not want to learn the formulas, just learn the ideas. Just like, for example, if you're studying mathematics, you might notice from an oral exam, sometimes you're not asked to do it with too much precision, but you need to show the idea of the proof. And here it's the same. You need to know Brownian motion, geometric Brownian motion, Ito's lemma, option price is the diffusion process again under Ito's lemma, slightly different parameters. The parameters are given by functions in the option Greeks, the partial derivatives. Then you do a delta hatch, and afterwards, you know. And as you can imagine, I'm pretty much interested in you understanding the notion that Black-Scholes is applicable to all derivatives. It cannot be solved for many exotic options and derivatives, but the framework can be applied to any type of financial derivative. That's why it's so darn famous, because it's very general. And you need Monte Carlo simulation, and you need finite differences for those exotic options. This is also the part I hate about most German textbooks. They simply present those ideas, and they do not really explain why those methods are needed. Monte Carlo simulation and finite differences do not make any sense for a plain vanilla option. You can just take, and as you can see from the examples in MATLAB, all those methods in best case scenario will yield the same price as black squares. So there's no need to do this. But in case you have an exotic option, you have no other alternative. Any other questions concerning the exam? Take a look at the tutorials, the previous exams, and I think you will be well prepared for the exam if you know the previous exams and those tutorials. Everything, of course, that is uploaded is also relevant. Okay, if you have no further questions, good luck with the exam, and well, take care during the vacation time after the exams. Thank you.